Welcome back to the next video in Tech 259. So far in this class, we've covered the basics of power and energy and work, and we've talked about calorimetry and phase changes. And the next thing that we're going to talk about is the laws of thermodynamics. And these form the backbone of our understanding of how thermal energy systems are going to operate. So for the next 2 days in this class session and the next class session, we're going to split up the laws of thermodynamics. There are actually 4 laws of thermodynamics, but they're numbered kind of funny, kind of weird. And there's a reason for that. So you would think it'd be the first, second, third, and fourth laws of thermodynamics, but actually it's the Zeroth first, second, and third laws of thermodynamics. And the reason that happened was because chronologically, the Zeroth law of thermodynamics is more fundamental than the first law of thermodynamics, but it was proposed and developed after the first law of thermodynamics. So they said, well, this really is more fundamental than the first law. So instead of renumbering everything, we're just going to call this one the Zeroth law of thermodynamics and keep the first law to be what it is. So we're going to not cover all of the laws of thermodynamics in one day. We're going to split them up a little bit. So it makes sense today to cover the Zeroth and the first laws of thermodynamics. And then in the next class session, we're going to cover the second and the third laws of thermodynamics. As it turns out, and you'll see this, as it turns out, the Zeroth law and the third law are almost trivial. I mean, they're important, but and they form the basis for other things. But there's very little I can really ask you about the Zeroth law or the third law, except what is it and what does it say? It's hard to make any calculation problems based on the Zeroth or the third law. So you'll see that. So it'll take us about 1 minute to cover the Zeroth law. And next time it'll take us maybe about a minute to cover the third law of thermodynamics as well. The ones that really deserve a lot of our attention are the first law and the second law of thermodynamics. They're I don't want to say they're the most important ones, but they're all important. But we're going to spend a lot more time, and they help us to understand the systems that we're interested in more than the Zeroth law and the third law of thermodynamics. So I'm going to do most of this on the document camera. So I'm going to switch over to the document cam, and we'll start talking about the Zeroth law and then the first law of thermodynamics. All right, let's start talking about the Zeroth law of thermodynamics. I think it's always nice to have a little bit of historical context to these types of things. So here's a little bit of context to the Zeroth law of thermodynamics. It was developed in the late 1800s to early 1900s, which you'll see is actually after the first law of thermodynamics, which led to the kind of weird numbering system. And it was developed mostly by a guy named James Clerk Maxwell, who you may have heard of before. He's a really famous scientist. He's especially famous in the field of electricity and magnetism, or electromagnetism. So you'll hear his name actually come up again in the second half of the semester when we study electromagnetism, because he's really a giant in the field of electromagnetism. But it's kind of interesting that he also worked in thermodynamics, and so he also gets the majority of the credit for coming up with this Zeroth law of thermodynamics, which is kind of the most fundamental one, which is why it was put in the numbering system before the first law of thermodynamics. So let's go ahead and say what it is. If 2 systems are each in thermal equilibrium. What does thermal equilibrium mean? It means that they're stable in temperature with no heat transfer between them. All right. So if they're in thermal equilibrium, if I've got two bodies right next to each other, like this is body A and this is body B, if they're in thermal equilibrium with each other, they're at the same temperature and there's no heat being transferred between them. All right, that's what thermal equilibrium means. So if two systems are each in thermal equilibrium with a third system, then, excuse me, then they are in thermal equilibrium with each other. Then they are in thermal equilibrium with each other. So this is kind of basically what we're saying here, excuse me, is that if A equals C and B equals C, then A equals B. It's kind of what we're saying here. So we're kind of like here, let's draw three systems, or just three bodies, because that's a simple system. So let's say that this is body A, and this is body B, and this is body C. All right, so what this is telling us is that if A is in thermal equilibrium with C, so I'll draw a little equal sign here, and body B is in thermal equilibrium with body C, so I'll draw a little equal sign there. So if A is in equilibrium with C and B is in equilibrium with C, then A is in thermal equilibrium with B. So we can automatically say that A is in thermal equilibrium with B because they're both equal to C. They're both in thermal equilibrium with C. All right. This seems kind of silly and kind of intuitive, but it wasn't for the late 1800s and early 1900s. What this really means, what does this mean? What it means is that all heat is of the same kind. Or in other words, AKA, there's only one kind of heat. There's only one kind of heat. Which almost sounds silly to us now. Like, of course there's only one kind of heat. What does that even mean? But it was not clear at all in the late 1800s and early 1900s that that was true. People didn't really know what heat was. You know, like now we understand that heat, in other words, thermal energy, is basically just the vibration of the atoms and molecules in a substance. But remember that in the late 1800s, early 1900s, people didn't even understand the concept of an atom, you know, or molecule. So the idea of vibrating things that are very, very small inside of a material or a system, that wasn't even something that they understood. There were a lot of different propositions for what thermal energy really is, but they didn't really know what it was. So it actually was pretty novel to say that, look, if A is in thermal equilibrium with C, and if B is also in thermal equilibrium with C, then we can say that A is in thermal equilibrium with B, because that was not necessarily intuitive at first. But there's only one kind of heat. That's what we can say. That's really it. That's all there is for the zeroth law of thermodynamics. All right, so we'll draw a line there. Like I said, it's kind of trivial, and there's not really a lot I can ask you on, say, a quiz or an exam about the zeroth law of thermodynamics. So let's go ahead and move on to the first law of thermodynamics. And a little bit of historical context about this one. This was developed by a couple of different people. The people that usually get most of the credit are someone named Rudolf Clausius, who also gets some credit for the second law of thermodynamics, and also somebody named Lord Kelvin. And the Lord Kelvin, he lent his name to the temperature scale as well, the degrees Kelvin, you know. That also comes from this person, Lord Kelvin. This is both in the mid 1800s, like around the 1850s. So this actually came before the zeroth law of thermodynamics. And I'm almost 100% sure that you've heard of the first law of thermodynamics before, but let's go ahead and write it down. What it says is that the total energy of an isolated system, and that's important, so let's underline that. The total energy of an isolated system is constant. Energy can be transformed from one form to another. Energy can be transformed from one form to another, but I'm sure you know what comes next, but cannot be created or destroyed. But cannot be created or destroyed. So we have an isolated system. Here's like an isolated system, and I'm going to draw these little hash marks around it, indicate that it's insulated, so there's nothing that can transfer from the outside to the inside. So this is maybe a gas or something inside there. That's a system inside of a box that is totally isolated from the environment, and the total energy content inside that box is constant. It cannot change from any form to another. So what this means is, for our practical purposes, what this means is that we can keep an accurate accounting of the energy transfer into and out of the system. Because if we have a certain system and we know that it has a fixed amount of energy in it, then if I can keep track of what is added or subtracted, so let's say it's no longer totally isolated. Let's say that I have a system and it's not isolated, then I can keep track of what I put into it. I can keep track of what comes out of it, and I can do an accounting of what comes in and what comes out. And so this is a helpful thing for us to do. And the reason we can do that accounting, what lets us do that accounting, is the fact that no energy is just going to be spontaneously created inside that system, and no energy is going to be spontaneously destroyed inside that system. So I can keep track of what's added, and I can keep track of what comes out of it, and I can do an accounting, and I can even write some equations, which we're going to do, to say that if I know what's added, I know what leaves, and I know the change in energy. So it lets us do some simple arithmetic to calculate energy additions and subtractions. And it turns out there are really only two ways. There are only two ways of adding or subtracting energy. There are only two ways of adding or subtracting what we're going to call internal energy. That's the energy internal to this system. And we can add it and we can subtract it, but we're keeping track of the internal energy of this system. There are only two ways of adding or subtracting internal energy to a system. What are those? Well, one of them is to add or subtract heat, which we usually abbreviate Q, capital Q. And the second way, you can probably guess, is to add or subtract work, which we abbreviate W. All right, so think back to the steam cycles that we talked about a little while ago. We talked about how in various different components we add or subtract heat and we add or subtract work. Remember that in a steam cycle, we add heat in the boiler, we subtract heat in the condenser, or heat leaves the system in the condenser. And in a steam system, we add work in the feed pump, and we take work out of the system in the turbine, which is really the whole purpose of this whole steam system, is to get work out of it, and we do that in the turbine. So if we want to keep track of what's being added to the system, that's one, and what's being subtracted to the system, it's very important to have a sign convention to understand what is an addition and what is a subtraction. So I've I've mentioned this kind of briefly once before, but I'm gonna make this very clear. So by modern convention, what we can say is that when we have a heat input, so we'll say a Q, which is a heat input, when we add heat to the system, Q input is positive. It's a positive number, all right? And the opposite is true. A Q output, a Q or heat output from the system is negative. So we're going to subtract from the internal energy of the system. And then the work is going to be similar. W work input to the system. When we do work on the system is positive. So that's like the work of the feed pump, that we're doing work on the system, on the steam cycle. That's a positive number. And the opposite, work output, so that's like what we get from the turbine, is negative. We're taking it away from the internal energy of the system. All right. So basically, you can kind of summarize that by saying that all net energy transfers, into the system are positive. Into the system are positive. And the opposite is true. All net energy transfers out of the system are negative. So that might seem kind of intuitive. I think it's fairly intuitive, but it's really important to note and be very clear about what's a positive value and what's a negative value, because we're going to start, manipulating these numbers and figuring out what is the work output from the turbine giving these other quantities. So it's important to know what is going to be a positive number and what's going to be a negative number. All right, so we can start to put this in mathematical terms. Basically, we're going to rewrite this. The total energy of an isolated system is constant. Energy can be transformed from one form to another, but cannot be created or destroyed. We're going to write that in a simple mathematical equation, which is probably even more useful to us than the words description. And so the first law equation is that the change in internal energy, which is delta U, is equal to Q, which is the heat, plus W, where W is the work added to or subtracted from the system. So this is a really important equation. This is the first law of thermodynamics equation. All right, so what do each of these mean? This is the work that is added to the system. Work input is positive. And if work was taken out of the system, then it'd be negative. So like the work of the turbine is negative because we're taking energy out of the system. This is the heat, right? So like we have up here, Q input is positive. So we're adding heat in the boiler. That's going to be a positive number. And in the condenser, we're taking heat energy away from the system. So that's going to be negative. And then delta U is the change in internal energy for the system. So think of, in the case of a steam system, think of the energy content of all of the H2O molecules in that system. Some of it's liquid, some of it's steam, but we're considering that to be an entire system, all of the H2O molecules in that steam cycle. All right, so what we can say, let's take this a little bit further. So some implications of this. Number one, if we had a truly isolated system, which is practically impossible in the real world to have a truly isolated system. So we'd have to have a fixed volume, and we'd have to have no heat transfer at all into or out of the system, which is really, really hard to do. In fact, pretty much impossible. But if we did, then that would mean the change in internal energy, delta U, equals 0. All right, so that's what it would mean. If we had an isolated system, we have no work being done or done by or done on the system, and we also had no heat transfer into or out of the system, then the change in internal energy would be 0, right? So that's, I think, clear enough. The next thing is probably the most important thing, though. And what we can say is that if we have a closed loop, if we have a closed loop, if our system is really a closed loop or a cycle, that's just another word to describe a closed loop, like our steam cycle that we've talked about a little bit. If we have a closed loop or a cycle, then when we're at steady state, I'm going to say at steady state operation, which means that we're not warming up our steam system, like we're not going to be increasing the temperature of the whole system. We might be increasing the temperature in some places and decreasing the temperature in other places, but the average temperature of the whole system is not increasing or decreasing. So we're at a steady state operation. So I mentioned in the past that it takes a while when you're first starting operation of a steam system, like any kind of steam cycle, it takes a while to warm up the whole system. But then once it's in steady state operation, then you're not changing the average temperature of all the H2O molecules in the system. All right, clear enough. So when we're at steady state, then delta U equals 0. Otherwise, if delta U did not equal 0, then our whole system would keep on getting hotter and hotter and hotter and hotter, or else it'd be getting colder and colder and colder and colder, depending on whether delta U was positive or negative. But we can say that if we have a closed loop cycle, then at steady state, delta U equals 0. And we also know that delta U equals Q plus W from up here. So what does that tell us? That this has to balance out. So the sum of all of our heat additions plus the sum of all of our work additions or subtractions has to equal 0. All right, so this kind of seems intuitive, but everything has to balance out. So this tells us that everything balances out. All of the heat additions, all the work additions, they always have to balance out and sum to 0 in the case of a steam cycle operating at steady state. They have to. But it's actually not just steam cycles that this applies to. It's actually any thermodynamic cycle operating at steady state operation. And there's actually more of those than you might think. I'll give you some examples of a couple of these. So one of them certainly is a steam cycle. So we can draw a really simple model of a steam cycle. But there are actually 4 of them in total. So I'm going to draw a couple of simplified examples of 4 thermodynamic systems. And the first one's going to be a steam cycle, which we also call a heat engine. It's one type of heat engine. All right, so we're going to have some kind of process. All right, so this is like the steam cycle. And we know we're going to have a heat input to it. The heat is coming into it from a high temperature source, which in this case is going to be the boiler for a steam system. So T sub H is T sub hot. It's the hot temperature reservoir, which in this case for a steam cycle is the boiler. So this heat input we can call Q sub H. It's the heat input. It's the Q coming into the system or the process. We've also got a heat output from the system, and it's going to a cold temperature reservoir, which is whatever fluid is running through the condenser or whatever is being used in the condenser to remove heat from the steam system. So we'll call this Q sub C. And then the last thing, which is kind of the most important thing, it's the reason why we do this whole process, is a work. All right. And what we can say is this is the net work output. All right. The net work output, because we know there's actually a little bit of work input for a steam cycle in the feed pumps, right? We got to put some work into it in the feed pumps. But the way we design this is that the work out in the turbine is much, much larger than the work input in the feed pumps. All right. So this is basically a simplified design of a simplified model of the process. And in this case, our cold temperature is what we might call an ambient temperature. So this is like the ambient temperature of the lake water that's being used to cool down this process in the condenser. Or, I mean, you could use any type of fluid or any type of air, but we would say that in this heat engine, the cold temperature reservoir is sort of like the ambient. And we're doing something else to create this hot temperature reservoir, like burning something or collecting solar thermal energy or nuclear fission or something like we talked about before. Lots of different ways to get a hot temperature reservoir. But basically, if we look at these arrows, this is coming into the system and these are coming out of the system. And what the first law tells us is that if we add this and this, because they're coming out of the system, they have to add up to this. So Q hot equals the net work output plus QC in the case of our simple heat engine. But that, like I said, that's not the only type of thermodynamic process. There's another one, there's actually 4 of them. So the next one is actually not very uncommon. It's called a cold heat engine. So it's very similar to this one, but the only difference really is that what we're going to say in the cold heat engine is that the T hot is actually the ambient temperature. And then we have our process, whatever that is. It could be a steam cycle or something. We have heat coming from the T hot reservoir. That's still going to be Q hot. We still have heat being rejected from the system. That's Q cold. And we have a cold temperature reservoir. But the difference here is that you got to use some mechanism here to get the cold temperature reservoir below the hot temperature reservoir. Otherwise, this heat is not going to flow. Heat is only going to flow from higher temperature to lower temperature. So somehow in this one, you need to get this cold temperature reservoir lower than the ambient temperature. It could be some type of refrigeration cycle or something like that. But it needs to be a lower temperature. And then we've still got our net work output, which is the output of the turbine. And then, well, we're taking the difference between the output of the turbine and what we have to put into it in the feed pumps. So this would work as well. It's not very common because usually it's easier to kind of artificially increase T hot by combusting, burning something, or collecting solar thermal energy or something like that. It's easier to increase T hot usually than it is to decrease T cold. Right? So the differences were that in this one, T cold is the ambient temperature. In this one, T hot is the ambient temperature. In this one, we're kind of artificially heating up T hot. In this one, we're kind of artificially decreasing T cold. But either one would work and they would achieve more or less the same effect. That's not the only 2 kinds though. These other 2 I'm going to draw are a little bit different. So let me draw it and then I'll name it so that maybe you can then understand and see what it is. All right, so here's our process. And in this case, we actually do work net, a net amount of work into the process. And then we have Q hot going up into a hot temperature reservoir. and that heat is coming from a cold temperature reservoir, where that is the ambient temperature. All right, so take a look at this for a minute. What's going on? Well, we're adding work to the system. We're doing some amount of work on the system. And as a result of doing that work, we're actually pumping heat from a cold temperature reservoir up into a hot temperature reservoir. All right, so where might you see this? Well, this is like a heat pump. This is a heat pump. So this is like if you had a cycle, and these do exist, like an air to air heat exchanger, or a geothermal system. This could be a geothermal system where your ambient is the T cold, let's say the temperature of the groundwater, and you're doing work on the process. That means you're like driving a pump or a compressor that's driving the refrigeration, the refrigerant, that's the working fluid in this system, and you're pumping the heat from the cold ambient temperature up into, say, your home. So T hot in this case could be the inside of your home where you're heating it with a heat pump. So T cold could be the outside air temperature, it could be the outside ground temperature, but this is what a geothermal or an air-to-air heat pump does. It requires work input. You're driving a compressor to drive a refrigeration cycle, and you're actually driving the temperature, the heat from a cold temperature reservoir up to the hot temperature reservoir in your house. The other one, the last one, is just a little bit different. Let's say that we have this process and we again put work into it. And now we're going to drive heat up to T hot, where now T hot is the ambient temperature. And once again, we're taking heat from a cold temperature reservoir. And that cold temperature reservoir is actually colder than ambient. So what is an application of this? This is actually a refrigerator, or a refrigeration cycle. So T hot is your house. That's the temperature of the air in your house. T cold is the temperature of your refrigerator, inside your refrigerator, or inside your freezer, something like that. Or this could be an air conditioner. This could be an air conditioner where T hot is outside your house in the summertime and T cold is inside your house in the summertime. We have to provide work to drive that compressor of the refrigeration cycle or of the air conditioner. And as a result of that work being put into it, you are driving or pumping the heat from a cold temperature reservoir to the ambient high temperature reservoir. Once again, if we look at any one of these processes, we could use the first law of thermodynamics, and we could say that we could write a balance, because whatever comes into the system or the process must come out of the system, and these have to balance. So in this case, we could say that whatever comes in, Q hot, equals what's coming out, QC plus work out. In this one, it's the same thing. We'd say that the input equals the outputs combined. In this one, our inputs are QC and work input, so those combined equal the heat output. And same thing here, work in plus QC equals the heat output. All right, so that's just a thermodynamic model of 4 different common thermodynamic processes. The last topic that I want to mention in this video is about the idea of efficiency. And we're going to talk more about efficiency in later classes, but I just want to get you started thinking about efficiency in this class. So in general terms, what is efficiency? Efficiency, no matter what kind of system we're talking about, efficiency is always equal to what is the useful output of the system divided by what is the total input that you have to put into the system. All right, that's the most general form of efficiency. What is the useful output divided by what is the input that you have to provide to the system. So you can kind of define what is the desired or useful output to these systems compared to what is the input that you have to put into the system. And it's the definition of efficiency might be a little bit different for each of these systems. For example, let's take this one first, even though we're not going to talk much more about heat pumps, for example, geothermal systems or air-to-air heat exchangers. We're not really going to talk a whole lot about them in this class. If you want to, you could do your thermal energy project on it, though, if you want to. But anyway, let's take this system and think about what would the efficiency be. Well, what is the useful output of a geothermal system? It's the heat that you're getting to heat your home, right? So Q hot, this is your useful output. This is really what you're designing the system to achieve. So this is your useful output. What's your input to the system? Well, this is actually kind of an interesting question. We can see really what the input is. Well, we're providing work in, and we're providing electricity to drive this compressor pump that does work on the refrigerant in this geothermal system, or whatever fluid we're using for this system. So we are doing work on it. And then we're also getting heat from the ground in the case of a geothermal system, right? Or the air in the case of an air-to-air heat exchanger. But the thing is, when you have a geothermal system or an air-to-air heat exchanger, you're not paying for the heat in the ground, right? Like that almost isn't really a consideration for you. You don't have to pay for that energy. That thermal energy in the ground is just there. And so a lot of times when people talk about the efficiency of a geothermal system, they actually ignore this right here because you're not paying for it. Unless you're designing the system, you barely have to even think about it. So a lot of times people talk about the efficiency of a geothermal energy system where they say, this is your output and this is what you have to put in. This is like the electricity to drive this pump for the compressor. And they ignore this altogether in their efficiency calculation. And what that ends up giving you is an efficiency that's greater than 100%. Actually greater than 100%. So you'll see quotes for geothermal energy systems where they say the system has an efficiency of 200% or 250%, something like that, which is wrong. I mean, the first law of thermodynamics tells you that you can't get out more than you put in because there's this balance of heat and work, right? But it's all in the accounting of this. So that's kind of an interesting side note. I remember when someone first told me that a geothermal system was 200% efficient, or maybe the first time I read that, I was like, whoa, what's going on here? But that's what it is. It's that they're taking the useful output as being the heat to your home, which is legitimate, but they're saying the input is the only thing you have to put into it is the electricity to drive the pump that does work on that system. So because this is bigger than this, you get efficiency that's larger than 100%. All right, so that's for a geothermal or a heat pump type system. We're going to spend most of our time in this class talking about heat engines like steam cycles. So what is the useful output and what is the total input required for this system? Well, for this system, the heat input is this, right? This is the amount of heat that you have to put into the system. So you gotta provide fuel of some sort to elevate the temperature up to T hot, which can then give us this heat input to the system, right? So that's our input. What is our useful output? This is also an interesting question because it actually depends on what part of the world you're in. If you're in the United States, or frankly, if you're in most parts of the world, the only useful output is this. This is the only output that we're taking advantage of. We're using this work output or the net work output to drive a turbine, and that turbine is connected to a generator, and we're converting that to electrical energy. And so ultimately our output from the whole combined system is electrical energy, right? So really in the US and in most parts of the world, the only useful output is this. But it is true that in some places in the world, like in especially Northern Europe and Iceland, and in some really cold places, they actually do use this. They actually do use this part for something called district heating. So this is a heat output from the system. So you could actually use that heat, put it in a piping system and pipe it around the neighborhood and use it to heat buildings and homes. So you can actually use that. And if you did use that and you counted that as a useful output, then your calculation for efficiency would look a lot different. You would seem to have a much more efficient system. But for our purposes in the United States, the only real output that is useful that we're using, I guess kind of unfortunately, is this, our net work output. So our input is this and our output is this. And so we can write a simple little equation for efficiency. Let's make it general first and then make it more specific. So in general, for any system, efficiency is equal to the useful output divided by, what do I want to call this? I think I want to say what you have to put in. All right. So it's not always necessarily the total input it's what you have to put into it. What you have to put in. All right. So let me give you another example. Let's say a light bulb. All right. Take a light bulb. What's the efficiency of a light bulb? Well, what's the useful output? The useful output of a light bulb is light, right? It's photons. Come on, focus there. Sometimes this thing doesn't focus very well. The useful output of a light bulb is light. It's photons. That's what we want to get out of it. It also produces heat, but that's not really useful for us. So we're not counting the heat that it produces. Even LEDs produce heat, some heat. Not as much as incandescents, but they still produce some. So anyway, that heat is not useful for us, so we don't count that in this equation. What you have to put into it, that's the amount of power or energy, depending on how you're looking at it, that you have to put into the light bulb in order to energize it. All right, so for a steam cycle or a steam system, our output is this, and our input is this. So what we can say is that the efficiency, and by the way, the symbol that pretty much everybody uses for efficiency is the Greek letter eta. It's kind of like a backwards 3, kind of backwards 3 and then rotate it a little bit. So you'll get some practice writing the Greek letter eta. And what the equation for efficiency is the work output. And technically, we should probably say that's the net work output. You know, in practice, we usually don't. In practice, we usually just say it's the work output. And usually that's fine because the work output of the turbine is so much larger than the work input in the feed pump that the work required as input to the feed pump is pretty much negligible. So this is a pretty reasonable equation, even if we just say it's the output, the work output, even if we don't specify it's the net work output, as in the turbine work minus the work in for the feed pumps. So anyway, work output divided by the heat input. All right, so that's a good equation to have in your back pocket. That is the efficiency of a steam cycle. Actually, it's one way of measuring the efficiency of a steam cycle. And we'll talk about a couple of different efficiencies later on. I'm going to stop this video there. That wraps up most of our discussion on the zeroth and first law of thermodynamics. The next video is kind of fun. I enjoy it because the next video is about perpetual motion machines. And one thing that the laws, not just first law, but the laws of thermodynamics tell us is that perpetual motion machines are impossible. They do not exist. But the exact reason why they exist depends on why they don't exist depends on which law of thermodynamics they violate. So if you propose a perpetual motion machine and it doesn't work because it violates the first law of thermodynamics, then we call it a perpetual motion machine of the first kind. That's what it's called. So in the next video, we're going to talk a little bit more about that, and I'm going to show you some examples of perpetual motion machines of the first kind. So I'll see you in the next video.